And Pierce, this is Dr. Jones checking in. This is a video lecture. It's for A&P 2, lecture test 1, video 6. And we're starting video 6 on page 14 of the note set, top of page 14, which for me this version looks like this, the neural layer, and at the bottom, page 14. Okay, so the neural layer, what did we talk about last? Last we talked about the neural tunic, the neural layer, which includes both the neural layer, which is the photoreceptors and the neurons, and the pigmented layer, which we already talked about the pigmented layer, right? That it has lots of melanin and it helps to absorb photons that have gone through the retina. So here's the pigmented part. And the photons go through these layers to be absorbed by these segments, the outer segments. And the photons that aren't absorbed by an outer segment and seen get absorbed by this pigmented part of the retina, and that keeps you from having visual echoes from photons bouncing around inside your eyeballs, which sounds annoying. Okay, and we talked about this part. Okay. Maybe I didn't talk about this part. All right, so the axons of all the ganglion cells in the eye converge at the optic disc, and they become the optic nerve, cranial nerve 2. Because the optic disc is made of axons and has no photoreceptors, it is a blind spot. And why do you not notice your blind spot? Well, one, you have two eyeballs, so the blind spot of one is seen by the blind spot of the, by not a blind spot of the other. Yeah, like that. And also your eyes make small tracking movements all the time. If you've ever tried to just stare at one thing for very long periods of time, you'll know that after a while you have an almost uncontrollable urge to glance away. Plus microscopic movements of the eye, moving what you're focusing around on the back of your retina. So all of those reasons. And then I have a note on clinical notes. While we won't normally cover the clinical notes in lecture or in the note set, you are expected to read the book. Specifically, you are also expected to read the clinical notes and know all of the clinical notes in each of the chapters covered on the test. Even if there are sections of the chapter we're not covering, I do expect you to read all of the clinical notes. Expect to see a few clinically related questions on every test, and especially on the final. Okay. Chambers of the eye. The aqueous humor, I'm guessing I have a picture for that. Oh, look, there's the optic disc. Here's the optic disc in a picture of an actual eyeball. And here's the optic disc in our drawing from the book. And ganglion cells, axons become part of the optic nerve, cranial nerve 2. Oh, and here is how you see. Let's see, I have these instructions written out somewhere. Okay, they're in the book, but I don't know. So you cover one eye gently. You never squish an eyeball, always like cup to cover. You cover one eyeball and focus on either the plus or the dot. I thought I had it written down in this note set, but it must be on a different page. We'll find it. But read the, it says in the book under the picture. So definitely spend a few seconds finding your blind spot, because like, oh, okay, there's a blind spot. And then you actually find your blind spot and then it makes sense. Some things make more sense once you've seen them for yourself. Okay. Let's turn on our laser pointer. There we go. The circulation of the aqueous humor, and we've got these lines here to show our circulation. So the aqueous humor is made by the ciliary body, and then it circulates through the posterior chamber, which is the space between the iris and the lens, through the pupil, which is a hole where there is not iris, and through the anterior chamber. And remember, the anterior chamber and posterior chamber together make up the anterior cavity. Anterior cavity is from the cornea to the lens. Anterior chamber of the anterior cavity is from the cornea to the iris. And then the posterior chamber of the anterior cavity is from the iris to the lens. So the aqueous humor, aqueous means agua, water. Aqua in Latin, agua, I believe, in Spanish. Q versus a G, same difference. And so the ciliary body makes it, and then it goes through the posterior chamber, through the pupil, into the anterior chamber, and out the scleral venous sinus, which used to be called the canal of Schlemm. So that's the circulation. Aqueous humor is secreted by the ciliary body and absorbed at the scleral venous sinus. And you can see two little tubes here, two circles. This is, of course, a round tube. It'd be like if you cut a donut, you'd get two circles, but really it's a tube. Donuts. Glazed donuts, sprinkled donuts. Filled donuts. Cream filled donuts with chocolate glaze. Yep. I usually use bear claws as an example just because it sounds funnier. But cream filled donuts with chocolate glaze sound good too. Okay, so aqueous humor. Off topic. Aqueous humor functions to, back on track, donuts. Circulate nutrients and wastes, maintain intraocular pressure, which we're about to define in a second, maintain the eye shape, and stabilize the retina against the choroid. So actually, technically, presses the neural part against the pigmented part. Intraocular pressure is the pressure in the eyeball, and the scleral venous sinus is a vein. Venous means vein, of course, and sinus is a type of vein, and it's next to the sclera, the white of the eye, so scleral venous sinus, and that drains the aqueous humor. Aqueous humor is being made all the time and needs to be drained all the time, sort of like CSF was last semester, where the CSF was being created all the time by the choroid plexus and had to be drained all the time by the arachnoid granulations. Same thing here. If the scleral venous sinus is slow in draining, then you get raised intraocular pressure. I think I'll bug to land on my nose. Okay. Raised intraocular pressure, which is termed glaucoma. Now, there are two types of glaucoma, acute and chronic. Acute happens all at once, where all of a sudden you can't see, and you're in the ER because all of a sudden you can't see out of one eye or both, but you're in the ER. Chronic, acute is always all at once, an event. Chronic is always an ongoing progressive thing. So chronic glaucoma, the intraocular pressure raises slowly enough that you don't notice it on a day-to-day basis. And by the time it's bad enough for you to notice it, you've already lost vision or done enough damage that it can't be treated effectively. So that's why every time you go in for an eye doctor's visit, they do that evil puff of air in the eyes. And they're like, why are you crying? Like, evil puff of air in the eyes. What did you expect? Not a fan of the glaucoma test, but it's necessary because without it, untreated glaucoma, again, by the time you know it's happening, it's too bad to be able to do much with. There are treatments for glaucoma. I think there are eye drops. I don't remember. Medicines. I don't know if it's just a pill or just eye drops or both, or they can go in and surgically drain the eyeball if it comes to that. Usually the goal in life is to avoid surgery where possible. So you need the surgery, you get the surgery, but try everything else first. General rule of life. Life advice with Dr. Jones. All right. Vitreous body. Oh, I did want to say with glaucoma that the excess pressure, because the fibrous tunic of the cornea and the sclera is so tough, that you don't get any ballooning of the fibrous tunic. What happens is you start to push the axons of the ganglion cells out the optic disc. So you're pushing the optic nerve out the back of the eyeball. And at 2 times normal pressure, you start to get tunnel vision from damage to the peripheral nerves, because at excess pressures against the cell membranes, you can't propagate an action potential. So that's why. Okay, vitreous body is a gelatinous mass that helps to, we need the next PowerPoint slide. Oh, evil glaucoma poof machine. There it is. All right, that's not the vitreous body. Still not the vitreous body. So in the posterior cavity is the vitreous body. And it helps to stabilize the shape of the eye. Again, it holds the neural part to the pigmented part. They're actually not connected. It's the pressure of both the aqueous humor and the vitreous humor in the eyeball that keeps the eyeball literally inflated and keeps the retina in place. When the retina pulls off, it's called a detached retina, and they go in and they surgically zap, 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 zap the retina to the pigmented part, which does cause small blind spots, but better than slowly losing your vision, slowly or quickly losing your vision over time. So does the vitreous body circulate? No. Is it replaced routinely? No. Is it replaced ever? No. Born with it. Okay. And the lens. Now we're ready for that next slide that we were on. No. There we go. Okay, the lens. Oh, page 15. I need to flip. Flip. Page 15, the lens. The lens is this thing right here. And its function is to refract. And refraction is when you change the angle of the light. There's like a tiny little fly that like landed on my nose earlier and just not landed it on my glabella. Okay. So the lens is held in place behind the pupil by the ciliary zonules, which in lab we call the suspensory ligaments, the new term is ciliary zonules. Either way, it's 3-dimensionally around the lens, holds the lens to the ciliary body. The primary function of the lens is, again, to focus visual images on the photoreceptor by refracting and changing the angle of the light ray coming in through the pupil. Have we had the see-through conversation yet? Okay. Look at the cornea. The cornea is the clear bubble in front of, anterior to, superficial to your lens, your iris and your pupil. So that clear bubble there, and that's completely see-through. And then behind the pupil, inside your eyeball, is a lens, which is also completely see-through. And then the vitreous body, gelatinous, see-through. And of course, the aqueous humor is like a liquid aqua water thing. See-through. You make like, you're completely see-through up to the retina. I totally think we need more see-through tissues. Be so cool. Okay, so the lens, one of our see-through bits, completely transparent. The lens actively focuses visual images on the rods and cones by changing shape, and changing shape is going to be called accommodation. Undisturbed, the lens is spherical in shape due to elastic fibers in the capsule. So on its own, the lens is a globe, a sphere, a ball. Okay. Cells inside the lens are called lens fibers, so you actually have see-through cells. Really. And they contain crystallins, which are transparent, see-through proteins. You make see-through proteins. Did you know? Now you do. And they're responsible for clarity and focusing power of the lens. Describe the stability of the crystallins. They are extremely stable, last a lifetime. They're remaining intact and functional for a lifetime without replacement. Have we had the with without? We haven't had the with without conversation yet. Okay, so see, the line over it is for the Latin word con, which means with. And then S with a line over it means seen, which is Latin for without. If I recall correctly, the Spanish word con means with, and the Spanish word seen means without. So if my Latin and Spanish are both correct, then this is one of the times where the Latin and Spanish are identical. Like water, the Latin is aqua, and I believe in Spanish it's agua with a G instead of a Q. Very similar, Romance language. Okay, so a cataract is a condition in which the lens has lost its transparency, where it becomes less see-through. And senile cataracts, of course, occur with age. Refraction. Oh, that's not next. Radiant energy is next. Radiant energy is any energy that radiates heat, light, radio waves, pretty much most of it. Give some examples of radiant energy. Oh, I had a whole list of these and my lost note set that must be at school. Okay, so the radiant energy, there's the electromagnetic spectrum of radiant energy, and then there's gravitational waves, which we have proven. They built this thing out in the desert with like a V and mirrors, and when celestial things happen, it changes the distance as measured by reflections of mirrors at the end of the, anyway, it's pretty cool. So gravitational waves are a definite thing. They were a theoretical thing, and then we're like, well, how can we test it? And then we tested it, and then we proved it happened. Fun. New science all the time. It's exciting. And so there's gravitational waves, and then there's electromagnetic energy, which is all the other radiant energy. So heat, light, microwaves, radio waves, the whole shebang. Okay, cell phone waves. Describe, draw wavelengths and amplitude. A wavelength is the distance between two peaks, and amplitude is the distance between the peak and the trough, trough being the bottom of the wave. So amplitude is the height of the wave, and the wavelength is the length of the wave. Okay, so who is Roy G. Biv? This is red, orange, yellow, green, blue, indigo, violet. So these are the colors of the rainbow, and the red should always be on top or it's upside down. There's a double rainbow, which is cool too. Oh, and question, what's the difference between, because we've got an indigo in here, and given the wavelengths, it seems like there's just kind of an extra color in there because there is. Indigo is just a dark blue purple, which, I mean, what about blue green? What about yellow green? What about yellow orange? But what about red orange? What happened was the guy who named the colors of the rainbow thought 7 was a magic number, like celestial religious magic number. And so therefore, since he was naming the colors of the rainbow, there had to be 7 of them. So that's why. Ha! Photon jokes. A photon checks into a hotel and is asked if he needs any help with his luggage. No, I'm traveling light. Because a photon is a packet of light energy, which acts simultaneously as a particle and a wave, which, to my knowledge, we don't quite understand yet, but it is. So that happened. I tell the science jokes kind of as part of your curriculum because if you remember the joke, you remember the science behind it. And often tell my kids the joke that night when I get home because it's fresh in my brain. And the funny part, because my in-laws live with us, is then my kids tell my in-laws the joke. Okay, that's not the funny part. The funny part is the next 10 minutes when they're explaining to my in-laws the science behind the jokes. So it's all about science jokes. True story. So that was page 15, and we are making progress, and I forgot to set an alarm. Poop. I wonder if there's a way to check the time without ending the arrow. Well, no, that's the next. Okay. No, that doesn't have the time on it because that one's not the recording. That one's just the video. Okay, we're going to keep going because it doesn't feel like half an hour yet. Let's do page 16. Okay, so focus or in focus is when something is on the, let me see, here. Focus or in focus is when the focal point is on your retina, when you can see it and it is not blurry. Okay. And then accommodation is changing the shape of the lens to allow you to see either close up or far away. Refraction, okay, that was not the picture I wanted. There we go, refraction. Refraction is when the light rays change direction get bent by a change in density. So here, the light rays reflecting from behind this glass of water, when they go through the glass, they go from the lighter density of air to the thicker density of the glass, and then the water um, bends the rays in such a way that it makes this cool design. It's just like if you stick a straw in the water, but it looks broken. That's refraction. There's reflection like off a mirror, and then refraction where the light doesn't go back the way it came, but it is bent. So, and you can see in this picture, let's go to laser pointer, that the light from this light source, this white bar in the picture, refracts when it enters the lens, enters the cornea, and then refracts again in the lens to focus together on the retina. So that is in focus because it's on the retina, not in front of the retina or behind the retina. Okay. The focal point is this point where the light rays converge. Do we have the words converge and diverge? Nope. Okay, pen. Okay. Converge, and we'll do this left to right like we're reading English. Converge is when the light rays come together. Diverge is when the light rays spread apart. And then parallel, that's the sign for parallel. P-A-R-A-L-L-E-L. So the math sign for parallel is these two L's, just like the two L's in parallel. And that's two lines that, like railroad tracks, will never meet, ever, because they're going the exact same direction. So they will never, ever touch. So next. Focal point is where the light rays converge. Here's your focal point. The focal distance is the length from the lens to the focal point. And you can see we have shorter and longer focal distances, and we'll talk about how to get that here in a second. And the focal distance is determined by three things. The distance from the lens, greater is a closer is a greater focal distance. The shape of the lens, rounder is a shorter focal distance. I've lost where the third one is. Oh, it's because there's only two. That's why. Okay. So astigmatism is when the curvature of the cornea or the lens is irregular. So maybe it's got a bump here or a divot here or something. And that causes an astigmatism, and there are special glasses for that that are kind of a pain to get used to. They say the contacts are kind of interesting too because they have to be weighted. And so there's like a little weight on one end so that they always point like the right part up. I don't know. I'm not a contacts person. So draw examples of light rays converging. Here you go. And diverging, spreading apart, and being parallel. There we go. Already did that. And then draw this picture. So the focal point is where they converge together, hopefully on your retina, not in front of it or behind it. The focal distance is the distance from the lens to the focal point, and we can change this focal distance with accommodation. We'll talk about that, converge, diverge, parallel. The effects of the shape of the lens and the distance of the object from the lens. So we have parallel lines. When a light is from a distant source, at least 20 feet away, then it's parallel when it hits the center of the lens. And so as we move from a distant light source to a closer light source, here the rays are diverging instead of parallel. And so the same amount of bend in the lens focuses further from the lens. So with a closer source, you have a longer focal distance. Because at a closer source, you have a more acute angle. So it just takes more to bend those rays. Okay. And then the other thing we can do is make the lens rounder. So you can see this lens is thicker across than this lens. And when we make it rounder, we allow for a more angular refraction, and that shortens the focal distance. So the rounder the lens, the shorter the focal distance. So the closer the light, the longer the focal distance, and the rounder the lens, the shorter the focal distance. Yeah. All right, so that was page 16. Let's see. Did that? I don't think it'll show me the length, the distance, I don't think it'll show me how long this is until I turn it off. So, okay, so we are going to shut this down and we will start with accommodation page 17 on the next video. I apologize for having zero idea how long this video is. We did finish 16, 14, 15, and 16. 3 pages is probably enough anyway. All right. So this has been a video lecture of Del Mar College, Dr. Jones. Oh, A&P 2, lecture test 1, video 6, note set pages 14 through 16. The education must go on. Thank you as always for tuning in. Dr. J out. After I find the command control escape. There it is. Have a good one.